In this video, we will discuss local linearization, where it comes from, and how it is applied in calculus. Local linearization is a way to make use of a tangent line. So we're going to start with an equation of a line. You might be familiar with point-slope form, y minus y1 equals m times x minus x1, where x1, y1 is a point and m is a slope. If you solve this for y and you add y1 to the right-hand side, we would get y equals y1 plus m times x minus x1. And then we can do a substitution here. We're going to replace y with L of x because we're going to use a linearization to approximate a y value. We can say this will be approximately equal to, now y1 we are going to use as our function value, and we're going to use it as the f value at a, the number we're working with, plus the slope at a, we'll call f prime of a times x minus that value a. So there's the form for linearization. I like to write the approximately equal to sign because it's a reminder that we're using linearization to approximate a value. Let's take a look at this example here. Use local linearization to approximate f of 0.1, where f of x equals x cubed plus 1. So I graphed x cubed plus 1 on a graphing utility. Now zooming into the point 0, 1, because I chose the a value of 0, which is arbitrarily close to 0.1, the place where we are approximating. So taking a look at 0, 1, and if you zoom in close enough, you can tell that that slope looks horizontal. So if I draw a tangent line through that point, it looks like it has a slope of 0. And if we write the equation of that tangent line, that equation of that line would be y equals 1. So what we're trying to do here is approximate the y value when the x value is 0.1, and I can approximate that on that linearization, on that tangent line. So if I imagine plugging in 0.1 on that tangent line for an input, that output value should be 1. In fact, all of those y values on that tangent line will be 1. So it's important to note, though, that that y value is not the same thing as the y value on that blue curve. It is on the tangent line. It is not on the equation of the function. So what we're trying to do here with linearization is to approximate a value, the value that's on the tangent line on the linearization, and we'll say that that is equal to 1, which is approximate for the function value. So in an example like this, when you have the function, which is not always the case, we can actually plug it into the function. If we do f of 0.1, now that would be strictly equal to, since we have the function which is x cubed, so we're going to take 0.1, cube it, and add 1 to it. And what we're going to get here is 1.001, which is a point that would be on that blue curve. Notice it's slightly above the linearization. So we have an error of 0.001 because the true function value would be in blue slightly above that linearization. But remember, the linearization is an approximate for a function value. We were able to approximate 0.1, so the linearization would be 1. Again, the number we would get from the tangent line. Let's look at another example here, and this one is important because we don't have the function value, so it's critical to do the estimate using the linearization. Let's write that linearization formula one more time. F of a plus f prime of a times x minus a, and the a is equal to 5. Since the information we have here is all based on 5, I'm going to rewrite f of 5 plus f prime of 5 times x minus 5. And we're going to plug in the x value of 6. So we want to approximate using linearization what the value at 6 would look like. And it would look like f of 5, which is 43, that's given, plus the slope at 5, 0.75, multiplied by x. Let's plug in the x is 6. 6 minus 5 is 1. 1 times 0.75 is 0.75. And then add 43, and we're going to get 43.75. Now remember, this is not f of 6. This is approximate to f of 6, since we approximated the point which would be on the tangent line located at a point 5, which is close to where 6 would be. So the linearization is an approximate value for f of 6.